All right, good afternoon, everyone. I see a few of you have already finished the assignment on the Connect, the Learn Smart assignment. That's great. It looks like in the Learn Smart modules, so far, if you complete the whole thing, you get all the full points. So as we go along through the semester, what I'll do is have probably different types of modules. The Learn Smart modules where you'll just always get full points if you go all the way through it. And then some more standard homework type problems where you may not get all the points. So depending on how you answer. The Learn Smart actually is a tool to help you refresh and learn the material. So it's less about answering every question right, more about going through the process of learning it. So I'll intermix that with more traditional types of homework assignments where you get only a few chances to try it and you get it right or wrong. About half of you haven't started the homework assignment yet, the Learn Smart yet. I just want to remind you that it'll go through Wednesday, this first assignment. I'll probably start the second assignment before Wednesday if you want to get started on that as well. And tomorrow, Connect is doing some upgrades on their system, so it won't be available tomorrow, just to let you know that. All right, so last time on Wednesday we were talking about aspects of structure and how we account for electrons, and we talked about formal charges, and you should be very familiar with formal charges and hopefully get to a point where you recognize immediately, based on the number of bonds to an atom and what would be expected based on valency, what the charges would be. So for example, in our nitric acid example, nitrogen has a formal plus charge and oxygen has a formal minus charge in those particular cases. We also talked about how we can draw the molecules in different ways, and the molecules that have the same molecular formula can be connected in different ways, and this is what we refer to as constitutional isomers, right? And depending on the number of atoms and the number of valency they have, you can get all kinds of different isomers available. This particular example, there are essentially only two constitutional isomers that you could draw that would be legitimate Lewis structures. Another concept we talked about Wednesday, which is one that I find often students have a difficult time grasping. And so this concept of resonance forms will come up over and over again as we go throughout the semester, particularly when we start talking about reactions with double bonds and triple bonds. Resonance forms are very, very important in that. For example, if you take the acetate ion here, our Lewis structure representation for accounting for all the electrons doesn't really represent the true structure of the molecule. And that's the key thing here. I just want to reiterate that when you have different resonance forms for a molecule, they don't exist like this. That's not what actually exists. That structure isn't what actually exists. What exists is something in the middle, a combination of those. And the relative contributions of the extremes of those structures we can draw depends on the relative energies. So if one of them is much higher in energy or much less stable than the other, it's going to contribute little in terms of that structure to the overall hybrid if you sum all those different resonance forms up. Okay? And finally, we talked about how to represent structures. And this was at the very end of the class. I just want to say a couple more things about line structures, just to make sure you all are aware of what everything represents. So when we draw organic molecules using line structures, keep in mind that we are not drawing the atoms for carbons and hydrogen. So if you just take a look at this molecule here, right? That line structure is representing this molecule. Notice all the carbons and hydrogens are not drawn. It's assumed that you know they're there. And the other thing you have to make sure that you assume is how many hydrogens are there to make up a total of 4 bonds. So for example, if you have an end of a molecule that has only 1 bond, so there's a carbon-carbon bond, what's left has to be 3 hydrogens. Okay, so you have to know how many are there. This carbon right here that I've just circled, this has 3 bonds to other carbons. carbon needs 4 bonds, so the 4th bond has to be this 1 hydrogen. Okay? So in line structures, we draw them, we don't draw the carbons and hydrogens, that's assumed in the lines, but any other group or functional group or atom we do draw. So for example, bromine, or something like an OH group. Now, look at this, for example, when we have hydrogens on other atoms besides the carbons, we do draw them in. So we wouldn't just put O, because that doesn't make sense, right? We know it has to be an OH or O something else. All right, and you can see how this type of structure drawing makes it much easier to represent larger molecules. I mean, can you imagine having to draw out the full Lewis structure for something like hydrocortisone or beta-carotene? It would be very, very tedious and cumbersome to do that. So you should be able to recognize, for example, this carbon. That carbon has no hydrogens on it, right? It has 4 bonds to other carbons. One of the things I see that students make the mistakes on is not recognizing that these ends are actually carbons. Those are all CH3 groups. Okay. So as you go along and you get more comfortable and more used to these types of line structures, I think it should all become much more intuitive. Okay. Well, let's move on and continue our review of general chemistry. We know that we can draw molecules in many different ways, but they have shapes to them in 3 dimensions. And that depends a lot on the hybridization, the types of orbitals, and the types of bonding it has. And if you just think about it for a moment, think about a simple molecule like water. Right? It has 3 atoms, 2 hydrogens, 1 oxygen. And if you think about how to draw that and get them as far apart as possible, you might think on paper you would just draw HOH in a straight line. And the angle then between the hydrogen, oxygen, hydrogen would be 180 degrees. But that's not the true structure of water. If you actually look at the structure of water, it's bent. Water has a bond angle from hydrogen, oxygen, hydrogen of 105 degrees. Okay? And so you should ask yourself when you see something like that, why? Why does it bend like that? Okay. Take a look at methane. Right? Methane, CH4, the simplest of organic molecules. If you're just to draw it out flat on paper, right, you could draw carbon with 4 hydrogens on it, and the bond angle between the hydrogens would be, represented here would be what? 90 degrees, right? But that's flat in 2 dimensions. We know methane is not a 2-dimensional molecule. It's a 3-dimensional molecule. So if you actually look at the structure of methane, what we find is that the carbons are attached to the hydrogens, but the hydrogens are spread as far apart as possible in 3 dimensions. Not in the plane of the board here, but in 3 dimensions. And so it defines the shape of a tetrahedron. Okay, so another thing about representing structures, you notice I've drawn one of these bonds with a bold sort of wedge and a bond with dashes. What that represents is that this bond is coming out of the plane of the board, and that bond is going back into the plane of the board. Okay, so that's trying to represent the 3-dimensional structure. This might be a little bit easier picture to see for that methane molecule. So it's a tetrahedron in methane. If you look at any HCH bond angle, they are all the same. They're 109.5 degrees. Okay. So if you look at this methane, it has 4 groups on it, and 4 groups all trying to get as far apart as possible, and in 3 dimensions attached to a central point. That would define a tetrahedral. Notice that the bond angle is very similar to water. Water had a bond angle of 105, right, between hydrogen, oxygen, and hydrogen. So maybe there's some similarities in the structure, and for the same reasons. What I didn't show in that water molecule before was the lone pairs that are on the oxygen. That's the reason why oxygen has a bent structure. If you just look at the hydrogen, oxygen, hydrogen, it's 105 degrees. But in fact, there are more groups on that oxygen, not atoms attached, but electrons. There are 2 lone pairs. And oxygen has the same tetrahedral structure as methane. Okay, in terms of the electrons, the reason why this tetrahedral structure is adopted is because the electrons are repelling each other. And so it's the bonds. You have electrons in the bonds or electrons in the lone pairs all repelling each other. And if they're attached to that central atom, they just try to get as far apart as possible, and that defines the tetrahedron. Okay, so this is what we refer to as the VSEPR model, or the valence shell electron pair repulsion model. And so in order to understand the structure, you have to realize that the molecule will adopt the most stable orientations of all those groups, the most stable arrangement attached to that atom that has the maximum separation of the electrons that are either in the covalent bonds or in lone pairs. Okay, so it's very important to recognize what atoms have lone pairs on them and what don't. Right? That's really critical. So if you were to take something like ammonia, let's look at ammonia. NH3. What would the structure look like? What would the 3-dimensional structure look like? Well, it wouldn't be a trigonal bipyramidal. It would be, it's a nitrogen with 3 hydrogens and a lone pair. Okay, it has a lone pair on it. So nitrogen also, or ammonia, is a tetrahedron. Okay, it has tetrahedral structure. Okay, it's just like water, just like methane. The only difference is that the about 109 bond angle changes just a little bit depending on if you have something else, how big that group is on there. So for water, it pushes those hydrogens a little closer because the lone pairs are repelling greater. But those are just small little changes in the bond angle. It's about the bond angles for a tetrahedron. Okay, what about something like borane? We take a look at borane, and BH3 we see has a planar structure. The hydrogens are all equal distance apart. The bond angle, hydrogen-boron to hydrogen bond angle, is 120 degrees. Okay, so what's different about borane from something like water or methane or ammonia? There's no lone pair, that's right. Remember, boron is to the left of carbon on the periodic table. It starts with only 3 valence electrons, and it has now 3 bonds. Now, it doesn't have an octet. Something to recognize, borane doesn't have an octet, but it has an empty orbital. It's missing 2 electrons in an octet. But that fits very nicely into our model using the VSEPR model, because the hydrogen-boron bonds, there are 2 electrons in each of those bonds, and they just try to get as far apart as possible. There's no repulsion from an orbital which is empty. Okay, there are no electrons in it. So if you have 3 points that are trying to get as far apart as possible, that defines a plane, and it's 120 degrees bond angle. Here's 120 degrees, here's 120 degrees, and here's 120 degrees. Okay, make sense? So this VSEPR model actually works pretty nicely. Just remember that it's electrons, whether they're in bonds or lone pairs, that are repelling. And if you think about 3 dimensions and how to move them as far apart as possible, that's what dictates a lot of the structure. Okay, now when we have organic molecules, we can have multiple bonding between the atoms. And in VSEPR theory, we treat those the same as if it was one group. So if you have a carbon-carbon double bond, that carbon-carbon double bond is thought about as one group. So this has, if you look at one of the particular carbons in this ethene molecule, it looks a lot like boron. The difference is that this double bond, which is an overlap of p orbitals, still has electrons, but we sort of count both of those together. So these also have about 120-degree bond angles. Actually, it's a little bit wider for the hydrogens and smaller for the other. But it has a similar structure. It's a planar structure. All right. And when we go to triple bonds, there are two of these side-to-side overlap p orbital overlap bonds, pi bonds. And what that does is it makes the carbon-hydrogen bond and then the carbon-carbon triple bond only two groups. They try to get as far apart as possible. That's 180 degrees. There's a molecule now that has 180-degree bond angle when you have triple bonds. Okay, we'll see this over and over again as we work more with organic molecules and these functional groups. Okay, there's another aspect of molecules. We sort of hit on this a little bit before about dipole moments. We talked about bond polarity, right? We know that if we have two atoms connected by a covalent bond and they have different electronegativity, right? Those electrons in that covalent bond are drawn more towards one end than the other. And I showed that with a little arrow, a plus on one side and an arrowhead on the other. That's a bond dipole moment. A dipole moment has both the separation of charge, the degree of the separation of charge, and the direction. That's the moment. So a dipole moment represents a separation of charge and the direction that the negative charge is going to. And we have that within individual bonds, but we also have that within whole molecules. Okay, so the molecular dipole moment is simply defined as the sum of all the individual bond dipoles in the substance that you're talking about. Okay, so it's important to recognize this leads to the polarity, overall polarity of molecules. We have molecules which are nonpolar, and we have molecules which have some polarity. That one end of the molecule might be more negatively charged than the other. Okay, so as a whole unit, the whole molecule, we can have a molecular dipole. A dipole moment, by the way, is represented by the Greek symbol mu, and its units are device, if you recall that from general chemistry. And it's important to recognize also, depending on the three-dimensional structure of the molecule, you can have molecules that have polarized bonds in them, but overall, the molecule itself is nonpolar, has no dipole moment. For example, carbon tetrachloride. Right? Carbon tetrachloride is carbon tetrachloride is a tetrahedron, and then each of these carbon-chlorine bonds are polarized bonds because the carbon is less electronegative than chlorine, right? So each of these has an individual dipole moment for the bond, with a plus charge nearer to the carbon, the electron density closer to the chlorine, and so we draw that dipole moment indicated by an arrow in that direction. But if there are four equal bonds spread out in a symmetric fashion around that central point in 3 dimensions, right? And you add those up, you take the sum of all of those, that equals 0. So carbon tetrachloride is a nonpolar molecule. As a matter of fact, it's a very good nonpolar solvent for organic chemistry. Although for environmental reasons it's been phased out because these damage the atmosphere. But if you compare that to something like dichloromethane, dichloromethane has 2 bonds to hydrogen and 2 bonds to chlorine. So they have bonds which are different. They have different dipole moments. So the dipole moments for hydrogen, since hydrogen certainly is not much different than carbon, it's a little more electronegative than carbon. The chlorines are much more electronegative than carbon, and so these would be weaker dipoles, these would be stronger dipoles, and if you sum all 4 of those bond dipoles up, overall that molecule is going to have a dipole moment. In this case, dichloromethane has a dipole moment of 1.62 device. We would call that a polar molecule, slightly polar molecule. There are much more polar molecules. And the dipole moment for the molecule is sort of in that direction. So the sum of all of that, all those negatives. Okay, makes sense? Okay. You've seen me draw lots of different arrows throughout the class so far. And this is, again, part of the language of chemistry. And it's important that we're all speaking the same language. When we talk about chemical reactions, we have various kinds of arrows that we can utilize to mean different things. It's very important to use the right kind of arrows to show what you're talking about. So you've seen me draw things like a reaction. Okay, and we have an arrow which represents a reaction. So here is an example of molecule A, which is being converted into molecule B. And so we have a reaction arrow, which has just a line with a arrowhead on one end. Right? You've all seen that. A different kind of arrow is an equilibrium arrow. This particular arrow represents back and forth reaction. So A is being converted into B, and B is being converted back to A. Okay. That represents a situation where both A and B exist, they're just being converted back and forth. All right, that's very different than resonance forms, as we just talked about. Remember, we have a special arrow to represent resonance forms. This is a single line with an arrowhead on either end. That means that is not an equilibrium arrow, it's a resonance arrow. Those two representations mean very different things. Okay? This means there's actually a reaction taking place going back and forth. The resonance arrow is representing resonance structures which don't exist. Right? What actually exists is something in between, a combination of those two extremes. There's no reaction taking place, there's no back and forth. So it means something different. And it's very important to use the right arrow to describe what you're talking about, because they mean different things to chemists. Another way you've seen me use arrows, though, is to describe reactions. Okay? And in this case, you see me use curved arrows. This is not a reaction arrow, it's not in between species. Generally, it's talking about the flow of electrons, where they are and where they go. So when we try to describe how chemical reactions are taking place and explain the mechanism and where electrons are flowing, we use curved arrows. And the arrows begin where the electrons were originally in the start of the reaction, and we show the arrow flowing to where they're going to end up in the reaction. So in this case, I've given you two simple examples of a molecule with a covalent bond, A bonded to B. And in this case, A and B break apart, and the electrons are ending up over here on the B. Right? So if I wanted to represent with a curved arrow how those electrons are flowing, I know the two electrons are here in this covalent bond, and those two electrons are ending up on B, and so I draw the curved arrow like that, starting from where the electrons were to begin with and where they're going to end up in the product. Okay? This representation tells you that you're taking electrons away from A and giving it to B. So actually what happens is you get an A plus and a B minus. Okay? Now notice I have another example here where instead of both electrons going to B, one electron went to A and one electron went to B. They've split apart in a homolytic bond cleavage to give what we would refer to as a free radical species. Okay, we have another way to represent the flow of electrons when it's only one electron moving. And that is to use an arrow, which I think your book refers to as a fishhook arrow, or a half-headed arrow. So if we have a covalent bond where there are two electrons in it, one of those electrons flows to B, so I'll draw it with just half an arrowhead. Looks like a fishhook. And the other electron flows to A. All right, that's the way to represent the electrons and how they're changing in this reaction. Okay, so depending on whether you have a full-headed arrow or a half-headed arrow, you're talking about 2 electrons or 1 electron. All right? I hope you've understood that all along as I've been showing these arrows moving in the class. So this, I hope, is not anything particularly new. Okay, there's a lot of situations where we use these kinds of curved arrows. When we talked about, we showed them in resonance forms when I tried to describe how electrons, you could imagine them flowing. But in reactions, so if you have, for example, a dissociation reaction, here is a molecule acetic acid. And if that dissociates, that is, the proton comes off, how might you draw the reaction, the electron flow arrow, the reaction flow arrow, and the products? So the product here is going to be O minus plus H plus, right? Dissociation of an acid. So how do you draw that? Well, simple. You draw the electrons flowing to the oxygen. Okay, so that's an example of using that, curved arrow. I can also show then also the resonance forms for this acetate by showing curved arrows. Notice my resonance double-headed arrow there. Okay, I can draw that. Another way to use curved arrows. This next example is a substitution reaction. I'll show you the products, and then I want you to see if you can do the arrow. So the product would be this. Those are the products of that reaction. How would you draw the curved arrows showing how the electrons are all flowing? Any idea?
The bond between carbon and Br, have that bond, so electrons go to the bromine.
Exactly. The bond between the carbon and the bromine, electrons will flow to the bromine. That's breaking that carbon-bromine bond. Okay? Or forming another bond at the same time.
And then have the lone pair from oxygen, one of them connecting to the carbon.
Right. A lone pair from oxygen, I'll just pick this one, connects to the carbon. So that's how I would represent that. The electrons flow, now in this case, if the electrons are flowing between 2 different molecules here. Hydroxide, electron density from a lone pair attacks the carbon and forms a new bond. Notice that's a new bond that's been formed over here. And the carbon-bromine bond breaks. Okay, this is what we refer to as a substitution reaction. You're going to learn this in great detail later on, I guarantee it. Okay. The last example here is a acid-base reaction again, and it's a protonation. And so something like you have HCl, acid, you have oxygen with lone pairs, which could be a base. You could draw it this way. And the products here would be this. And notice, I start with 2 neutral molecules, and if I've broken the bonds this way, I end up with 2 charged molecules. Overall, though, we have a positive ion and a negative ion. Its overall adds up. Okay? Make sense? This is how we talk about reactions, and this is how we discuss reaction mechanism, and I'll be using these kinds of arrows over and over and over again. So recognize that the beginning of the arrow are the electrons that you're using to either form or break a bond, and the arrowhead goes to where they're going to end up. Yes, question?
For the chlorine, hydrogen chloride, what is it going that way around?
The electrons in the hydrogen and chlorine bond, the question is, why do the electrons go to the right instead of to the left?
It should be pointing towards the chlorine.
Oh, sorry, yeah. I'm broken the bond, and since that's the only atom there, it's kind of assumed, but I guess it would be better to represent this a little more clear. Oops, a little more clearly like that. Is that what you're saying? It means the same thing. Yeah. No, it's going to the core. Okay, any other questions on this? Reaction arrows? All right. I want to now cover acid-base concepts, because what we've been talking about here are some of these reactions, acid-base reactions. And a lot of reactions we talk about, it involves acid-base chemistry. Protonations to activate compounds to do further reactions. And this idea of electron flow and where electrons start and end up is also critical here. But just to remind you of some of the background on acid and base chemistry, right? We have various definitions for acids and bases. Arrhenius first described this as an acid being a substance which ionizes. So you have a heterolytic bond cleavage, a substance which ionizes in water to give protons. Okay, so it's not, protons are acids. And a base, the converse of that, a base is a substance that ionizes in water to give hydroxide ions. So M is just a generic symbol for a metal, for example. So if you have sodium hydroxide, it'll ionize to form hydroxide ions. Or proton, if the proton comes off, it'll ionize to form hydroxide. But then you also form proton, right? If M is a proton, if you're talking about water, what do? Do you call that by Arrhenius definition an acid or a base? So the Arrhenius definition was a good one back in the day, but there are some limitations to it. A better definition for acid and base is the Bronsted-Lowry acid base. It's important also to know that protons don't just become protons floating around as free protons. Bronsted-Lowry recognized that. We do have some concepts of strong acids and strong bases, and it depends on various aspects. So when we talk about an acid-base reaction, right, H bonded to A is some anion. It could be HCl, HBr, H acetic acetate, right? It could be a lot of different things. That dissociation of the proton and the anion is an equilibrium. And we define this as using a pKa, which is related to the acidity constant, which is just the amount of the equilibrium which lies towards the right side, right? This is the equilibrium constant. In this particular case, since we're talking about an acid-base reaction, it's an acidity constant, or Ka, which is the concentration of the products over the concentration of the reactants. So if Ka is higher, right, what does that mean? Which side of the equilibrium are we lying more on? To the right. If we have more products, in this case H plus and A minus, Ka will be higher, Ka will be larger. If this acid is stronger, you'll lie more to the right side. Okay, so the stronger the acid, the higher the Ka. Usually we represent this as the pKa, or the minus log of the Ka. So that number, the pKa, when we talk about pKa, it's actually the converse. So the lower the pKa, the stronger the acid. So Ka and pKa are inversely related. All right. We have some general definitions of strong acids and weak acids. Strong acids will lie far to the right side of this equilibrium, or ionize essentially completely. Weak acids might lie more to the left side of this equilibrium. It's more complicated than this because, as I said, HA don't just break apart to form free protons. There's something else involved. And for every acid dissociation, there has to be some base or something that's accepting that proton. And that's where Bronsted and Lowry provided what I think is a little bit better definition of acids and bases. The Bronsted-Lowry definition says that an acid is a substance which donates a proton, and a base is a substance that accepts a proton. Okay? So in this equilibrium, you have some acid HA, or generic acid here. It's not just dissociating on its own. We know that if we put that in water, if we put HCl in water, you don't just form H+. You form hydronium ions, H3O+. Okay, that proton is being accepted by water. So if we really represent that equilibrium with a proper equation, HA plus H2O gives H3O plus and the A minus, right? And the Ka reflects that hydronium ion concentration times the anion concentration over HA. Okay, products over reactants. And we define these different sides of the equations depending on how we've written it. So we refer to the species on the left side of our equation, the one that gives up the proton as the acid, the species which accepts the proton as the base, and that always generates on the right side of the equation something which had gained that proton, which we refer to as the conjugate acid, and what had given up the proton as the conjugate base. And if you think about it, if you were to go from the right side to the left side, this would be donating the proton, so that's why it's the acid, and the A minus would be accepting the proton, that's why it's the conjugate base. Now, if I were to switch this reaction around on the paper, if I were to put H3O plus and A minus on the left, and HA and H2O on the right, it's the same equilibrium. But our definition of acid-base, conjugate-base changes because this refers to what's on the left side of the equation and this refers to what's on the right side of the equation. That doesn't necessarily say which side it lies on at the equilibrium. Okay, that depends on the acid and base strength. Okay, and if we look at that case, water could accept a proton. So water can behave as a base. But water can also behave as an acid. It has protons on it, right? In this case, if you take the reaction of NH2 minus and react it with water, the reaction proceeds like that. Notice my reaction arrows? So that would form NH3 plus OH minus. Notice again on the left side of the reaction I have overall one negative charge, and on the right side I have overall one negative charge. Okay, so now in this example, which is the acid and which is the base? Well, obviously the water gave up a proton. So the water is the acid, and NH2 minus is the base. Okay, and on the right side of the equation, what's the conjugate acid? NH3, right. Conjugate acid is NH3, and the conjugate base is hydroxide. All right, so why is water acting as an acid in this case, but acted as a base in my generic example? If I were to take HCl, water would act as a base. If I take NH2 minus, water is acting as an acid. Why? It has to do with the relative acid and base strengths of what it's reacting with. So if you have something like water or something like ammonia, depending on what it's reacting with, it could either give up a proton or accept a proton. So you have to consider everything involved in the reaction. That's why I think the Arrhenius definition was specific in water, but it didn't even talk about hydronium ions. Okay, and that acid strength is not going to be an acid if it's in something else. Okay, so it's important to have a good idea about how to relate acid strengths, and I don't need you to memorize specific acid pKa's. What I want you to do is try to learn generalities of how structure and molecules relate to their acidity or basicity. So here's a few acids. I've shown you some of the acids, their pKa values, and remember, the lower the pKa, the stronger the acid. And if it gives up a proton, what the structure of that conjugate base would be. Okay, so if you look at something like water, water is neutral, right? That's what we consider as neutral. So down here at the bottom of the periodic table, I have, the bottom of this table, I have water. Water has a pKa about 16, 15.7 to be exact. That is the pKa, or relating to the acidity constant of giving up a proton, this acting as an acid to form hydroxide. All right, if you look at something like acetic acid, which is right above it, has a pKa of about 4.7. So acetic acid is significantly more acidic than water. How much more acidic? How many times more acidic? Oh, these are pKa's, right? So let's just say 15 and 5, or 16 and 5. That's 11, right? A difference of 11 in pKa units. That's 10 to the 11th more acidic. Right? That's a lot. Oh, I'm sorry, that's, yeah, 10 to 11. Notice some of these other things, like HF has a pKa of 3.1. If you have water which has been protonated, it can give up a proton much easier than water itself could, right? Because it would become neutral in the conjugate base. So obviously hydronium ion is going to be a stronger acid than water itself. Something like HCl is a pretty darn acidic acid. HCl has a pKa of about -4. Okay, so those are some examples of things which are more acidic than water, and to quite some extremes as well. Here are some examples of molecules which are less acidic than water. Water pKa of 15.7. Most alcohols have similar pKa's, but usually slightly less acidic, but in a similar range. It's 17 is just 2 pKa unit, or 1 pKa unit different than water. That's the proton on the oxygen which we're talking about becoming an alkoxide as the conjugate base. There are things which are much, much less acidic. Some things which don't give up a proton very easily. Those are things that are usually carbon-hydrogen bonds or carbon to other elements which hold on to them much more tightly. So for example, ammonia, as I showed you in that last example, ammonia has a pKa of 36. That's essentially not acidic at all. The NH2 anion is a very strong base because of it. Another concept you need to keep in mind is that since we're talking about an equilibrium from the acid to its conjugate base, the acid, the stronger the acid, that means it gives up the proton easily, right? So the conjugate base that results from giving up that proton should be weaker. The stronger the acid, the weaker the conjugate base of that acid. It should be a more stable conjugate base. And the weaker the acid, the stronger will be the conjugate base in terms of its basicity, ability to accept a proton. And that's what we see here. Ammonia. Hydrocarbons are, you can't take a proton off hydrocarbons without something else helping it. Methane has a pKa of 60. 60. Notice something like this molecule, acetone, and I'm just focusing on this one carbon-hydrogen bond. Obviously, there are 3 here and 3 here. They're all identical. But if I were to take that proton off and generate a minus charge, it's easier to do that from this molecule than it is from methane, right? It's not that you can't remove protons from carbons. You can, depending on the other structural features which make it more acidic or less acidic. Actually, this CO double bond greatly acidifies the adjacent positions. And we'll learn more about that later as well. Okay, so let's think about this now in terms of that reaction of NH2 minus and water. Well, you can see now why that equilibrium, or that water, acts as an acid instead of a base. Look at the pKa of water here is 15.7, and the pKa of ammonia is 36. Okay. In that reaction, let's see if I can go back to that for a second. Oh, I don't have it all drawn out today. In that reaction, right, the pK of 36 for ammonia and 16 for water. Which is the stronger acid? Water. Which is the weaker acid? Ammonia. So obviously this reaction is going to lie far to the right side, and this is going to be much more basic than this is. That's the converse of the acidity. So you don't really have to know a lot about basicity. It's exactly the opposite of the acidity. Water becomes hydroxide relative to ammonia becoming NH2 minus. Okay, this is going to be a strong base, weak acid, weak base, strong acid in this particular pairing of molecules. Okay, now a lot of things affect the acidity of molecules. A lot of structural features. So one of the things that affects this is bond strength. So when you talk about taking off a proton, the strength of that hydrogen whatever bond is very important. The weaker the bond strength, obviously the easier it can give up that proton, the more acidic it will be. Electronegativity of the group the proton is attached to, and there's also further aspects of that electronegativity. So if you think about giving up a proton and then you have formed a conjugate base, right? The stability of that conjugate base will matter as well. The more stable that conjugate base, the lower in energy, lower in reactivity, more stable, the easier it will be to form. So the easier it will give up the proton. So the more electronegative atom, if it's more electronegative, it can give up the proton easier. You can also stabilize the electrons on that conjugate base by delocalizing it through resonance. So if you have more resonance structures available, you can easily form that negative charge and it can be then spread out. That's more stable. So it's the same thing if you think about the stability of the conjugate base which is formed in an acid-base reaction.
So the weaker the bond.
Weaker bond, stronger acid. So if you look here, HF, HCl, HBr, HI. When you go from stronger bond to weaker bond, the pKa goes lower and lower, which means the acidity gets higher and higher, the acid strength. So HF, 3.1, all the way to HI, which has a pKa of minus 10. That's quite a bit of difference in acidity. Stronger acid to the right, weaker HX bond. Electronegativity, this is comparing the acidity of a bond from hydrogen to an atom going across the row of the periodic table. So if you think about a CH bond versus an NH bond versus an OH bond versus an FH bond, right? That's just going right across the periodic table. Notice how different the pKa is. The only thing we're changing really is the electronegativity of the atom it's bonded to. So methane, not acidic, with a pKa of 60, all the way down to HF with a pKa of 3.1. Okay, so that greatly affects acidity. And electronegativity is more than just being bonded to that specific proton. Electronegativity also extends through bonds. This is what we refer to as the inductive effect. So if you take a look at this acetic acid, we're not changing at all what the proton is attached to, but we're changing a bond further away. So X, if it's hydrogen, acetic acid has a pKa of 4.7. If you go all the way to fluorine, more electronegative atom, the pK goes down to 2.6, it becomes more acidic. And that's because fluorine is not only electronegative pulling on this bond, but that polarizes the whole molecule even further away, pulling electron density towards it, making it a proton easier to come off. I mean, that's an additive effect. So if you compare fluoroacetic acid at pK of 2.6 to trifluoroacetic acid, it gets even more acidic. And that does drop off precipitously as you go further and further away from where the acid and proton is being generated. Okay, we're going to talk more about this on Monday, finish up acidity, and then move into chapter 2, where we'll really start to talk a little bit more about organic structures and hydrocarbons. All right, have a great weekend, and don't forget to start working on that homework.